Okay. So chapter 7, section 1, number 5. So if you graph this cubic curve, x cubed minus x times 3, it's 0 at minus 1, it's 0 at 0, and it's 0 at plus 1. And the curve looks roughly like that. So this is the curve y1. And y2 is the x-axis. And they want you to set up a definite integral to give the area of the region between these two curves. So there's this part above the x-axis and this part below the x-axis. So the area is equal to, well, the area from here to here on the left-hand side, that's the integral from minus 1 to 0 of 3 x cubed minus x, the top minus the bottom, which is 0, dx. That's the area of that. And what's the area of this? This is the integral from 0 to 1. It's the top minus the bottom. The top is 0, and the bottom is this. So this becomes
I think that's why.
The integral of 3 x cubed minus x dx. So it's not asking you to do the calculation, just set up the integrals. And these are the integrals. Is that clear?
Very clear.
Professor, can you please go back again to the part where you was graphing the y1, like with a different example, please?
Me graphing this cubic curve?
Yeah, but with a different example, just a graphing way.
No, I don't understand what you're asking.
Yeah, the way you graphed it, and the way, can you just try with like a different example, just a graphing part, not the integration part?
Oh, I'm sorry. So maybe the sound is a little bit garbled, but are you asking about where this graph comes from, or are you asking about another problem?
No, I get it. The way you did it with the graph, and the way you graph the line, the curve, using the y1, 3 x to the third negative x. But the way you just did it, but I'm just asking, can you just do that graph part only with a different example?
You say, I don't understand. When you say that graph with a different example?
Yeah, can you just like graph something else, but just that step? I just didn't get that step, the way you graphed it.
Well, first of all, the graph is, the picture's in the book.
Okay, sir.
So even,
Okay,
so I mean, I know how to graph it, but even if I didn't know how to graph it, that's not necessary. They're giving you the graph in the text.
Okay, then that's perfect. Okay.
If you're just going to analyze this though, what you would say is, well, x cubed minus x, if you factor out an x, that's this. If you factor it again, you get x times x minus 1 times x plus 1. So this is equal to 0 when x is 0 or plus or minus 1. So that gives you the fact that this curve is 0 here, here, and here. And you should know that every cubic curve with a positive leading coefficient has a graph that looks like that. So you know the graph has to go up, down, and up again.
Okay,
and that's what you know to do this problem. But they do give you the picture in the textbook.
Okay. Yeah, and also a question that's really not related to this, but so the final, so I had the chance to look at the final on the Lehman website, of I think it was 2019, and the final wasn't talking about integer, it was only more about series and convergence.
Wait, I'm sorry. You looked at the final exam for this course That's on the math department website?
Yeah, the final exam before the one that was taken, I think 2019. It was in
Right.
2019. They
So
just
that
asked.
doesn't apply to us in any way. So that is the departmental final
Okay.
that's been given. But, and that's because during the regular academic year, there might be, 10 different sections of Math 176. And they're all given
Okay.
essentially the same final. But in the summer,
Okay.
there's no departmental final. I make up the final.
Oh,
And
you. Oh,
also the
okay. Okay.
final
Okay.
is a little bit different when you're doing things online.
Okay, because because I took Math 175 online. It was a departmental final that we used. So I was just wondering if calculus
Right,
was the same.
right. Also, last term I taught 175 and I used the departmental final online. But in the summer, there is no departmental final.
Oh, okay. So you're just gonna. Okay. 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 So then we have time to work on that. Thank you.
Mhm.
Okay, Professor. Can you do the same chapter, question 45?
In section 7.1,
Yes.
okay. 7.1, you said number 45?
Yes, there's like two equations.
Yep, okay. So let's see what the instructions say. We can't use a graphing utility, but we can find the area of the region and then use integration on the computer to calculate it. So let's just see what we can do without the computer. So we have two functions, y equal the square root of 1 plus x cubed, and the other function is y equals 1/2 x plus 2, and x equals 0. So what is this thing going to look like? So the line y equals 1/2 x plus 2 is a straight line with y-intercept 2, and it goes up with slope 1/2. So this is the line y equals 1/2 x plus 2. And the square root of 1 plus x cubed, when x is equal to 0, that has the value 1. And this is some curve that is increasing. And we need to know, when do these two curves intersect? That is, when is it the case that the square root of 1 plus x cubed equals 1/2 x plus 2? So if we square both sides, 1 plus x cubed is equal to 1/4 x squared plus 2x plus 4. Okay? 1/4 x squared, 4, and 2x. Or x cubed minus 1/4 x squared minus 2x minus 3 equals 0. So it would be good to know when these are equal.
Professor, where did you get the 2x?
Here?
Yeah, I only see 1/2 x plus 2.
No, I'm squaring both sides. Right? I want to know when these two curves cross. And then when they're equal, then the squares are equal and we just get a polynomial. In fact, if I just make a lucky guess, if I let x equal 2, the square root of 1 plus 2 cubed is the square root of 1 plus 8, which is the square root of 9, which is 3. And 1/2 times 2 plus 2 is 1 plus 2, which is 3. So these curves cross when x is equal to 2. So The region cut out by these two curves is this region from 0 to 2. And the area is going to be the integral from 0 to 2 of the top of the curve, 1/2 x plus 2 minus the bottom of the curve, square root of 1 plus x cubed dx. So that is the integral that describes the area. The top minus the bottom. And that integral, I think, is too hard to be done by hand. But if you were using Maple, you could do it.
Maple.
Yes. But since Maple is not required in the class, then you can't do it.
Okay, Professor. So I'm good at differentiating and all that, but how you think is the best way to master the?
I'm sorry. Can you speak more clearly? Or
Okay, so
louder?
I say
Because
that I'm
it's
good
hard to
at
hear.
differentiate. Yeah, I say I'm good at differentiating and all that, but in integration, I have like a little problems and all the understanding. And I've been doing a lot of exercises to practice myself. But what do you think is the best way of like more understanding or quicker way?
Well,
Because I'm a mathematician,
so
so it's really gonna affect me.
differentiation is easy because there are rules that always work.
Yeah.
Integration is hard because you do not have rules that always work. You don't have there's no formula to do most integrals. You have various methods that might work, and you have to experiment and try one thing and then another thing and
Yeah, and check.
develop
Yeah.
some experience and skill. But it's not that the only rule for learning how to integrate is to do a lot of problems, study the examples in the book and the lectures and the homeworks, and just get a good feeling for what's going on. But it's just a matter of, it's like an athlete training for a sport. It's just a lot of practice that
Yeah.
gets your skill level up.
Okay, thank you.
Let me just tell you one thing about tomorrow. I'll send out an email about this. For tomorrow and only for tomorrow, instead of a problem session from 3 to 4, the problem session will be from 5 to 6. There are a couple of students who work during the day and can't get on at either 10 o'clock or 3 o'clock. So I said tomorrow, I'll have the problem session from 5 to 6, so they have a chance. You still have a problem session at 10 a.m. Any other questions?
Yeah. For chapter 5, no, not chapter 5, lesson 3, homework, which is section 5.7.
Yeah.
For number 27, it's different for the 4th edition. I know we went over 27, but for the 4th edition, it's a different one. And
Yes. Probably. Well, the answer is I don't know because I only have the 5th edition.
okay, yeah, I'm just saying that before you get just so you know, it might be a different number.
Oh, that's no problem. No, I understand that Some people have addition 4, some have addition 5, some have addition 6. And the important thing is just that you do problems. And if they're not exactly the same, that makes no difference. They still cover the material.
Okay. So could we go over that question?
Which one? In section
There's,
5.7?
Yeah,
Which number?
27. It's
And what
the
is-
integral of the square root of x over the square root of x minus 3 dx.
Okay, so that's fine. Then in the 5th edition, that's number 9. So this is 5.7, sorry, number 29. So that is the integral of the square root of x over square root of x minus 3 dx, right? Is that the problem you want?
Yes.
Okay. And again, it's the first thing to do is to pay attention to the hint. The hint says that you make the substitution u equal to the denominator. So the denominator is the square root of x minus 3. So du dx is equal to 1 over 2 times the square root of x. Or another way to write that is that du, or let me write it like this, dx is 2 times the square root of x du. This says the square root of x is u plus 3. So this is 2 times u plus 3 du. So it looks like if I make these substitutions, what do I get? I get square root of x, which is u plus 3, dx, which is 2 times another u plus 3, du, over u. So this looks like 2 times the integral of u squared plus 6u plus 9 over u, or 2 times the integral of u plus 6 plus 9 over u, du. So this is maybe the hard part, so let me just double check. We have square root of x over root x minus 3 dx. And the book says, let u equal root x minus 3, which means square root of x equals u plus 3. Du dx, if you differentiate that, you get 1 over 2 root x. So dx is 2 root x du, which is 2 times u plus 3 du. So when I make my substitutions, root x is u plus 3, dx is 2 times another u plus 3 over u. So I get this polynomial. I get a half u squared plus 6u plus 9 times the natural log of u plus a constant, and then I substitute in u, and I'm done.
Okay, thank you.
Sure. Is that it? Okay. I started the recording a few minutes late, so just for the record, the first page of problems in this problem session is this. Just computing some integrals. And this was the second page. So they are recorded for posterity. Okay, see everybody who wants tomorrow morning. Bye.
Thanks.
Thank you, Professor.